I'll be doing another example of exponential Fourier frequency, exponential Fourier series, and it's a corresponding frequency spectrum. But before moving on to that new example, let me clarify something on the previous example we did. These were the Fourier coefficients, all this mess here, and we were finding the magnitudes of all those guys. Here's what I want to make clear that I didn't make clear before. The magnitude of this whole thing, I can take the magnitudes of each factor individually. Every the factors mean things that either multiply or divide. So the magnitude of this whole thing will be the magnitude of -1 to the n times the magnitude of sinh pi divided by the magnitude of pi times the magnitude of this complex number up here divided by the magnitude of this number, 1 plus n squared. And any real number, the magnitude is just the absolute value. And if it's a positive real number, the magnitude is just a number. So this -1 of the n, its magnitude is just 1. So it didn't even show up down here. Hyperbolic sine of pi is a positive real number, so that just shows up as sinh pi. Pi is a positive real number, that just shows up as pi. 1 plus any number squared, I mean n is real, in fact it's integers. This is just a positive real number, again it just shows up as itself. And then this complex number, it's the Pythagorean theorem. It will be the square root of 1 squared plus n squared. And the rest is as I did it last time. So let's do another example. Here's the function. Our job is to find its Fourier series and sketch its Fourier spectrum, its frequency spectrum. Just this number that is only defined from -1/2 to 1/2. And it's just 1 from -1/4 to 1/4, 0 everywhere else. But it's defined from -1/2 to 1/2. So what is P? P is 1/2. So here is, I'll do this C sub n first. And here's the formula for the Fourier coefficients. So if P is 1/2, I'm just going to integrate from -1/2 to 1/2, right? So I put my limits of -1/2. Nope. This is a sloppy mistake. Sloppy mistake that many students make. They just plug in, darn it, plug in P right off the bat. But the function is 0 up into -1/4, and then from 1/4 on up, and 1 in between. So the f of x will be 1 from -1/4 to 1/4. So be careful with those limits. And at this point, we're just integrating a function that's basically e to the ax. You should know how to do that. You don't need a table. Divide by the a part. You still have e to the ax left. Evaluate between the limits. Actually, right here, you should notice something. If n were 0, you'd be in trouble. You have to divide by 0. So we're going to have to treat the n equals 0 case as a special case. So evaluate it between the limits, and you might start getting the eye to see that this is going to be some kind of sign. If I would switch terms, and I could do that by multiplying by -1, or just bringing this -1 in. And then for the sign, I need to divide by 2i, and I have a 2i or I2 out here. So I'll break up what's up front here. Separate the 1 over n pi from the 1 over I2. The rest of it, so you can recognize this part, hopefully, Start recognizing that in this case it's a sine, whatever this exponent is without the I in it. These are the Fourier coefficients. Now what about this n equals 0 case? Well, I still integrate from minus a fourth to a fourth. And there the f of x is just 1, so I'm just integrating 1 from minus a fourth to a fourth. I get a half. So the whole Fourier series is this thing in general. So it's a half for the n equals 0 case. Then I sum over all the other infinite number of n's except n equals 0. This coefficient times e to the minus p. P was e is a half here. So when I divide by half, multiply by 2. That's where I got this exponent there. Anyway, now for the frequency spectrum of this guy. Here are all the c sub n's except n equals 0. For c0, it's just a half. So its magnitude is just its absolute value, which is the 1/2. For reminders, the p was a half, which means the fundamental frequency is always pi over p is 2 pi. So the fundamental frequency in this case is 2 pi. Here was the general Fourier coefficient. You can simplify a little bit. If I'm doing it for negative n, I would have a negative in here, but negative of the sign makes it the opposite sign. But I'd have a minus n out here, so the two signs cancel. So I could replace these n's with absolute value of n. It doesn't change anything. So let's start going through them. For the 0 term, it was just a 1/2. N equals 1, or plus or minus 1, it's going to be 1 over pi, because pi is a positive real number, so I don't have to change it. And then the absolute value of the whole sine pi over 2. Sine of pi over 2 is just 1. So we're left with 1 over pi. For plus or minus 2, n equals plus or minus 2, I have 1 over 2 pi. They're both positive reals, so their magnitudes are what they are. Then the absolute value of sine of 2 pi over 2, which is the sine of pi, which is 0. And in fact, any even n, you're going to get some integer number of pi, which is always 0. The sine of some integer number of pi is 0. So for all the even n's, the magnitude is zeros. Let's move on up to 3. Do it for all the odd n's. It'll be 1 over the 3 pi, absolute value of sine of 3 pi over 2. And if you look at it, all these odd guys are either going to be plus or minus 1. So their absolute values are always 1. So all that matters is what's up front here. So I'll get 1 over 3 pi. Then for the next odd one, or c plus or minus 5, it'll be 1 over 5 pi, etc. So now I could sketch all these on the frequency spectrum. There's the C0 term, the C1 term, C2 term, C3, C4, C5. It only has values at integer numbers of the fundamental frequency, which are 2 pi. So the units, if I wanted them to be radians per second, this guy would be 2 pi radians per second. This would be 4 pi radians. This would be 6 pi radians. 8 pi, 10 pi per second. I'm going to quickly go over odd and even functions. You haven't seen this before. This is what it means to be an even function. You change the sign of the argument and it doesn't change the value. What it means to be an odd function is if you change the sign of the argument, it changes the sign of the value. Graphically, even means the left side is a mirror image of the right side. And odd means if you flip the right side to the left and then flip it again around the x-axis, it looks like that. A function doesn't have to be either even or odd. It could be neither. And it has to be defined on a symmetric interval to even be considered as either even or odd. And here's where things are nice. For one thing, when you take an integral of an even function, you can look at it. The area under the left side is the same as the area under the right. So you can just integrate from 0 on up and multiply by 2. For the odd, it's even simpler. The two areas cancel each other out. If you integrate an odd function over a symmetric interval, the answer is 0. If you add two evens, you get an even. If you add two odds, you get an odd. If you multiply two of the same thing, whether it's even or odd, you end up with an even. Multiply two different things, even or odd, you get an odd. Cosine is even, sine is odd. X to the n is even if n is even, and odd if n is odd. Here's a few examples. We're supposed to find if the given function is even or odd. So let's say this is the given function. You could algebraically show that it's an even function. Here's a case, show that this guy's odd. Plug in minus x for x, crank it through, and we show that it's minus x. Algebraically show that it's odd. Here's an example that's more complicated. Here's the function. Determine if that's even or odd. In this case, to me, it's easier to plot it and look at the graph. Because if you do it algebraically, you have to be careful. It's not just the function itself, it's these limits. You have to do some inequality algebra. It's a little confusing and tedious. So I think it's better to graph it. Here's another case. It's only defined from 0 to 2. If it's not even defined on a symmetric interval, it's neither even nor odd. This helps us simplify calculations sometimes. We did this example earlier. Are these two functions orthogonal to each other? Well, let's see. X to the 2 is an even function. 1 is x to the 0. Even plus an even is still even. X to the 3 is an odd. If I multiply an even times an odd, I get an odd. If I integrate an odd function on a symmetric interval, I get 0. So yeah, these guys are orthogonal. Actually, it would have been orthogonal on any symmetric interval. It didn't have to be -1 to 1. So we'll do more next time. We'll get into the trigonometric Fourier